Hello everyone, welcome to Conf42 Rustlang 2025. My name is Vamsi Karanam and I'm thrilled to be here to talk about something I have been personally passionate about, combining the power of Rust with AWS cloud services. Over the next several minutes, we will explore how Rust's performance, safety, efficiency make it a great choice for building cloud native applications that scale reliably. Instead of just theory, we will walk through a flowing example system step by step so you will leave with a clear mental model of how this can apply to a real world workloads. When you build on AWS, scale is always central. Applications may need to handle millions of events, thousands of concurrent requests, and unpredictable workloads. At that level, every milliseconds of latency and every MB of memory counts. Rust combines predictable performance, similar to C or C++, with compile time guarantees that eliminates common runtime issues. For Lambda functions or ECS stars, small binaries reduce start times, and lean memory usage cuts costs. This blend of performance and safety makes Rust an excellent choice when you care about efficiency and reliability. Let's compare Rust against other popular languages in AWS. Go is a strong for Lambda and containers thanks to Go routines, but its runtime is bigger than Rust. Java has massive ecosystem, but cold starts and memory overheads are costly. Node.js offers fast development, but struggles with CPU-bound workloads. Python is unbeatable for prototyping and ML libraries, though it slows down at scale. C delivers raw power, but manual memory makes it error prone. Rust balances performance near C with safety and compile time guarantees. That combine that combination makes Rust stand out for cloud workloads. Where does Rust shine? For Lambda, small binaries equal faster cold starts. The borrow checker enforces memory safety, preventing bugs before deployment. With Tokyo, you can run thousands of async calls to AWS services without overwhelming threads. That reduces CPU and memory, lowering costs in Lambda, ECS, and EKS. Strong typing ensures requests are valid at compile time, preventing misconfigurations from ever reaching production. But Rust isn't perfect. Compile times can be long in large projects. Ownership and lifetime have a steep learning curve. The ecosystem is maturing, but Java and Python have more polished libraries. Tooling for Lambda is improving, but Python and Node still offer more templates. And Rust favors explicitness over dynamic metaprogramming, which is safer but less flexible for quick experiments. Being aware of these trade-offs makes adoption decision realistic. The AWS SDK for Rust provides strong support. Each service is its own create, so you import only what you need. Shared configuration handles credentials and regions securely. Built on Tokyo, it's async first, making it efficient for input output. With retries, pagination, and streaming built in, developers can focus on value rather than boilerplate. To make this concrete, let's build a file ingestion pipeline. A user uploads to S3 and event flows through EventBridge into SQS. Workers process it, DynamoDB stores results, and observability keeps watch. This example mirrors real-world patterns and highlights Rust's value at each step. Step 1. Upload files. With Rust SDK, you gain compile time assurance that requests are valid. Async lets you upload many files concurrently without blocking. This builds confidence that what you send to AWS S3 is correct and efficient. Next, triggering processing. EventBridge sends S3 events into SQS. Rust workers consume messages, safely deserializing them with CERD. Async workers scale out efficiently, letting you process hundreds of events in parallel without adding threads. This is where Rust async runtime shines. For compute, we apply to Lambda. Rust binaries are small, giving faster cold starts. Execution is predictable and efficient. With async, a single function can manage multiple tasks. Compared to Java or .NET runtimes, Rust lambdas are lighter, cheaper, and faster. After processing, we persist results. In DynamoDB, Rust builders enforce correctness at compile time. Async queries let you scale to thousands of operations. The system stays responsive even under heavy load. Observability is essential. With the tracing crate, you add structured spans into async workflows. Pair with OpenTelemetry and metrics stream into CloudWatch. For errors, anyhow, or the errors capture detailed context. Together, this makes debugging faster and operations clear. No AWS system is complete without security and deployment. Use IAM with the least privileged roles and KMS to encrypt sensitive data. For Lambda, cross-compile to muzzle for small static binaries. In containers, multi-stage builds strip unnecessary dependencies, shrinking image size and improving security. To recap, Rust compile time safety prevents runtime bugs. Async first makes it perfect for input-output workloads. The modular SDK is easy to adopt and end-to-end patterns map naturally. Compared to other languages, Rust's blend of performance and safety is unique. In closing, Rust is ready for cloud. It combines system-level performance with strong safety guarantees, making it ideal for AWS workloads at scale. The SDK provides the tools, and our example showed Rust across AWS landscape. If you are building next-generation cloud-native apps, Rust is not just experimental; it's production-ready. Thank you, and I hope this inspires you to try Rust in your AWS projects.